First of all, good afternoon, everyone. Thanks for joining the session on Introduction to Icepack Classic and its overview. So, we'll start the session. So, basically, what we are going to cover in today's session is Introduction to CFD, Ansys Solutions for Electronics Thermal Management, Ansys Icepack Classic, overview of capabilities, and multiphysics workflow with Ansys Icepack. So basically, you might be thinking why in the icepack part CFD is there. That is because the icepack solver works on the fluid. So that is a CFD solver on which icepack thermal electronic cooling works. So before starting with that, we'll just see a little bit intro like what CFD is. Then we'll go with the solutions for the electronics thermal management. After that, we'll see the general capabilities what are present in the Ansys Icepack Classic version, basically specifically, and then we'll see what are the different multiphysics associated related to the Icepack and what are its capabilities, and then we will go over the tool and we'll see. I'll showcase you a small demo. I'll give you an introduction on the tool also, how the UI is and how the tool works. So I'll be covering that also. So starting with the introduction to CFD, like what CFD is. Basically, CFD refers to the computational fluid dynamics. So basically, CFD is a science of predicting the fluid flow, heat transfer, heat and the mass transfer, all the chemical reaction and its related phenomena. So basically, wherever your fluid flows are involved, your mass transfer, heat transfer is involved in the phenomena. All those kinds of simulation comes into a particular domain or physics known as CFD. So basically, this is fully related to the fluid flows. So how the CFD works. So basically, CFD works on the numerical equations which are based on the conservation of mass, momentum, and energy. So these are three equations are the pillar of CFD. So basically, when we talk about the solution part, how does this get the equations get solved? So basically, your differential equation, partial differential equation for the conservation of mass, momentum, and energy gets resolved through your mesh node points, right? So this is how the CFD works. So basically, what are the different stages where you can use the simulation, whether it's a CFD, whether it's structural simulation, or whether it's an electronic simulation. So when we say about thermal simulation, so at what point of time we can utilize the simulation capabilities? So basically, you can utilize this at the various steps, starting from conceptual studies of new design, where your focus is for the develop design and development of a new design from scratch. So at that point of time, you can go ahead with the CFD or let's say any of the simulation tool based on the application and the product which you are using it. Then after it comes towards the second step, that is a detailed product development. When your uh, focus is oriented towards the detailed development. So at that point of time, you can utilize the CA tools. Apart from that optimization, so you're already having one of the developed product. You want to further optimize it more to increase its efficiency. So at that point of time, you can go ahead with CAE tools. Apart from that, troubleshooting is there. So you already have let's say you have already developed one of the product and now you identify like okay at this point of time uh, at this location there is a hotspot being generated, so I need to check it further and I need to optimize it, or let's say you need to figure out in what ways we can reduce the hotspot region. So that will come under your troubleshooting part. And then again, of course, you can, if you are redesigning new project or any of the components at that point of time, you can always go have the utilization of a CAE tool. So basically, when we talk about the analysis, so basically what and how analysis helps it in our day-to-day life is it complements physical testing by reducing the total efforts and cost requirement of for experimentation and data acquisition. So let's say you are developing one of the product. For example, let's say you are manufacturing a SMPS box, right? So you come to know like this is how the variations are in the fans, exhaust fans which are placed into the SMPS box. So you have to redesign it, you are designing a new product or you are trying to optimize it. So at in simulation, when you are going with the simulation part or you have identified a hotspot zone which is near to your fan location. So you want to reduce that. So there are possibilities, possibly two ways. If you can go with the higher CFM fan for the exhaust fans, or you can have a design change, right? So how CFD will help you here, or your thermal management will help you here is you can do your simulation, you can replicate your physical testing with the help of tools like Ansys CFD is there, or let's say Icepack is there, which is specifically for your electronic component coolings part. So you will give all the boundary conditions like this is how my flow is coming, this is my heat source region, or and let's say this is your hotspot region. Here you have defined that okay, there is no cooling channel, and you have given a certain FAM as FAM RPM as an it will act as an exhaust, right? So in that case, when you go with the CAE results or CAE simulations, you will come to know like you will identify the location. Now, what you can do is you will again go and change your CFM, or either you will increase or decrease. So let's say you have increased your CFM. So now you can identify like, okay, my hotspot region is now slowly disappearing. So this is one of the way how CAE can be used. If you are not using CAE tools, the ideal way will be you will change the fan, you will manually go with the prototyping, you will add the fans, you will test it, then you will again come, you will make some of the modifications, and then again you will test. So basically idea here is to reduce the number of physical testing and replicating those physical testing in your system itself. That is virtually you can replicate the physical testing. So this is how you can utilize the CAE tools, whether it's CFD, mechanical, or let's say your electronic tools. So this is how the system works in the background for Icepack solver. So basically for any of the simulation which will go along, the simulation consists of three major steps. That is pre-processing, processing or solving, and post-processing. So when we come talk about pre-processing, there are two major steps for each and every simulation, whether it's CFD, mechanical, or it's electronic simulation. Pre-processing will consist of CAD cleanup part, CAD cleanup and meshing part. Right. So in CAD cleanup, we generally remove the unnecessary components which won't affect our simulation results. Then we discretize the domain into small finite volume, control volumes. Right. On the right hand side, there is one of the geometry of pipes you can see. So you can see along our grids are drawn. So this is nothing but this is we have discretized the domain into small control volumes. So control volume is highlighted over here in the cubical manner. So now on this control volumes, the set of general transport equation which consist of mass, momentum, and energy equations, and so on, depending upon the requirement and the physics enabled during the simulation. So this equation gets solved over the control volume nodes. So this is basically how the numerical data is being resolved at the background. So coming towards the next step is Ansys solutions for electronics thermal management. So when we talk about the electronics or let's say thermal management, there are different dominant modes of heat transfer. So what kind of thermal simulation is the tool capable of doing? So when we specifically talk about ice pack, so you can see there is in the center green part is there that consists of Ansys ice pack. So for electronic coolings, all the modes of heat transfer is available in icepack, that is conduction, convection, radiation. And apart from that, CHT is there that we'll be seeing in the coming slides. That is nothing but basically the conjugate heat transfer. All these three modules are also available in CFD solution, whereas that is also known as Ansys Fluent and Discovery simulations. So conduction, convection, and radiation models are available for Ansys Fluent Discovery simulations as well as Ansys Icepack simulations. Whereas if we talk about the ANSYS mechanical simulations, only convection and radiation models are available. There is no source for the convection. So coming towards, there are majorly the three basic version, different versions of ANSYS Icepack. Is one of them is ADT Icepack, Icepack in SI, and then there is a classic Icepack. So what we'll be focusing in today's session is classic Icepack, which is more focused and oriented towards the thermal management and uh, the tool which users can use are the mechanical, thermal, and electrical engineers can use this tool to understand it more in a better manner. So on the top on side, you can see there are three different UIs. So the first one in the UI is the interference is for the AEDT spec. The second one is for SIVY spec, and the third on the very right top corner, that is for the iSpec Classic. So now when we talk about the classic iSpec, what are the different kind of simulations which we can do? What are the capabilities? Whether it's a single phase, multi-phase, whether you can go ahead with the trace mapping, joule heating, solar load modeling. So these are the various capabilities which will be presented over the coming few slides. What are the different capabilities? How you can perform your multi-coupling, multi-physics coupling is there. Whether you can go with the ECAT support, MCAT support or not. So these all we will be seeing in the coming slides. So basically, this is what ANSYS done in ANSYS Icepack Classic. All the two simulations which you are seeing, the simulation of drone and the system box. So when we talk about any of the thermal management system, or we want to focus is on the thermal management side. So basically, what are the different modes of heat transfer available? So we already know that in classic, all the three modes of heat transfer is available. Apart from that, conjugate heat transfer is there. So basically, when we talk about the conjugate heat transfer, that heat transfer is considered during your when there are two different phases. Let's say your solid phase and fluid phase is there, or fluid solid phases are there. From there, the flow is traveling. So in that case, CST analysis comes into the picture. Apart from that, there is also one additional capability, that is joule heating. When we talk about the traces on the PCB, all the traces and tracks which are present over the PCB, that will definitely have some of the electric potential or current flowing through them. So due to that, the heat generated throughout that path, that is basically a traces that can be seen, observed. So that will come under the joule heating part. Now, when we talk about the convection part, natural and forced convection, both the options are available. When we talk about the radiation, thermal and solar radiations are available. When radiation is there, we can also go ahead with the solar load calculator, which will be already having the solar load data, which that is basically heat flux, or else you also have an option to load your heat flux. So let's say you are already having the data of solar radiation, at what particular time your solar rays are behaving, what is the heat flux generated over the period of time, and how it's varying with respect to time to time. So that also you can give an input in terms of your UDF. So you can enter it in the profile and you can go ahead with your own data as well. Now, when we talk about the heat transfer, the flow part comes into the picture, whether your flow is turbulent or laminar. If it's turbulent, then what are the different turbulent models are available? So there are many turbulence models that are available in Classic. So basically, all the turbulence model those are available in Fluent are also available in Classic. Basically, you are having your K omega SST model is there, your K epsilon model is there, two equations model are there. Then one equations Sparta-Salmara's turbulence model is also available. When we talk about any of the simulation, so there are basically two major types of simulation analysis, basically steady state and transient state. So when we talk about the steady state, we are not focused regarding the time dependency. So what simulation can be done in the steady state is, let's say you want to analyze the heat flow in your CPU, which everyone is using in their offices, right? So you want to analyze how your thermal behavior is taking place, or what is the maximum heat which is the system is producing. So if we go around with the steady state simulation, what it will happen is, let's say you are given the solution for 2000 iterations. So it will show you the last of what are the results of the 2000 iteration when your flow is steady. So it won't give you the intermediate results. So if your focus is time dependent, like what's happening, how the flow is behaving with respect to, let's say, 0.5 seconds, 1 seconds, 1.5 seconds, 2 seconds. If you want to see your behavior with respect to your time intervals, then we need to go and perform the simulation in the transient analysis. After this, what are the additional capabilities apart from the steady state, transient state? Are the multi-phase options is also available. When we talk about multi-phase, so there are basically when our system is consisting of more than two fluids coming in. So when we say fluids in the electronic system, that is basically generally considered as the cooling channels for the cooling purpose. So let's say you are simulating with your coolant is air, natural air. So in that case, that is a single material. But what if your coolant is of combination of two or more fluids? Let's say you have designed a cooler with coolant with let's say 50% water and 50% of glycol. So in that case, multi-phase comes into the picture. So what it will do, it will take the properties of both the fluids and it will give the ratio, it will give it in input as such a way the you want to define it. Let's say you want to define water as a 30% and glycol as 70%. So you have that capabilities to regulate the things inside, control the things, control the ratios of the two fluids, or let's say if there are three fluids, you have that controlling. Apart from that, parametrics and optimizations are there. So how parametrics and optimization can help is when we talk about the parametrics. So let's say on the right hand side, you are seeing one of the uh, simulation of a PCB box is there, enclosure is there, in which one fan is there. Let's say this fan is placed over the heatsink. So let's say, for example, it is consider is this is an exhaust fan and it's uh, throwing out your hot air, hot gases outside the domain. Or if you are considering it as a cooling fan, your flow will come into the heat sink. So let's say we want to see whether the same fan with the different RPMs, how it will be performing. So when we talk about the different RPM, the flow rate will also vary. So there are two ways to perform this kind of simulation. One is you manually go and change the fan RPM at and you perform the individual simulations. So let's say you are varying your RPM of the fan from 50 RPM, 100 RPM, 150 RPM. The first way is like you can go with the one simulation, you can perform everything. You can go with the 50 RPM, you mesh it, you set up the full case again. Then you replicate this case, you change the RPM, then you perform your meshing. Again, you go with the solution part. This is one of the way. Second way, here parametrics comes into the picture. You can always perform the geometric parameterization, and you can define RPM as a parameter, and you can change it RPM, and you can give your values. You don't have to perform the simulation every time. That's once you give the different parametric values, the system will itself perform the simulation. So this is the other options. This is how you can proceed. Then coming towards the species transport. So when we talk about the species transport, chemical kind of reaction modelings, or let's say there is a wind tunnel in which there is a fire taking up place, how your smoke is propagating from one place to another place. So this kind of simulations are also possible with the help of Icepack Classic. Basically, these kind of simulations are done in the data centers when there is a sudden fire in any of the components, and how the smoke is propagating to the other areas and how the smoke is affecting the other components. So this kind of simulations can be done using the species transport model is there. Then again, reduced order modeling is there that will help you to perform your system level of simulation. And then coming towards the multi-physics coupling. So you can always couple your iSpec results into your iSpec result into your mechanical and other related phenomena. So that we'll be seeing in the coming slides. So when we talk about the simulation of electronic components, what are the modeling capabilities across all the scales? So when we talk about across all the scales, like at what level you can perform the simulation, whether it's a component level or a assembly level, or let's say a system level. So you can perform your electronics cooling simulation from the very component level, that is you can perform it on the chip and die side. You can then go ahead with your IC packages, or if you are already having your board assembly or backplane assembly, or let's say you are having a system level of system level solution, system level model is there. So in that case, you can go with the system level. So depending upon each of the things, it's from component to assembly level, you can perform your simulation at any point of interval. So let's say when we talk about the system level, so system level includes your supercomputers, data centers are there, or let's say an open environment is there. So you want to consider. So here are the few of the examples of the system level of simulations on the right hand side. Coming towards the tools, that is basically the UI and the primitives. So what are the iSpec primitives? Primitives are the uh, your shortcuts, you can say. If we talk about in the simple language, there are multiple shortcuts which are available to create your geometry in iSpec itself. So when we talk about the shortcuts, which are what are the different types of models which are already available. So let's say if you want to create an assembly, your assemblies are available. So under assembly, if you drag and drop any of the components under assembly, it will act as a full assembly. Then there are network regions. You can create the networks on your board through your components. So network junctions you can create. Heat exchanger design is already available. Openings is available. Periodic is available. Grills, sources, your PCBs are available. Enclosures are available. Plates, balls, blocks, fans and blowers, your heat sinks, packages, and a lot more. So these are few of the primitives which are already present inside the iSpec classic. So you just have to drag and drop and or let's say you just have to give your coordinates to the particular region. Let's say you want to model a fan. So you can double click on fan and give the coordinates and axis where you want to create a fan. Or let's say you want to create an enclosure, you need to select the enclosure and you need to create an enclosure. So when we create the system will ask for the two of the points, that is in all the three directions. If it's 3D, it will ask the direction, what is your start point in X direction and end point. So when it says start point, so your enclosure will start from that particular point and it will end at the end point. So these are the few capabilities which helps us to speed up the modeling part in iSpec Classic. Apart from that, this also captures the information, geometry properties. So when we talk about the geometry and properties, specifically, it will ask us the whether your block type which you are creating the geometry, whether it is solid, hollow, fluid, or it's a network component. So these options are available as you can see over here. So coming towards the supported CADs. So basically, what if you don't want to create the CAD inside the iSpec? So what are the other ways? So you can also go ahead with the other CAD tools. Basically, your MCAD support is there. That is basically your mechanical CAD. You can import your geometry through Space Client. So let's say you are working on any other tool. Let's say if you are working for a mechanical tool, let's say you are working on a SolidWorks or CATIA. So you can import the step file into the space clam and then you can link up the geometry in this way. So your geometry is directly getting transferred from mechanical CAD to your iSpec part, right? Apart from that, you can also import the ECAD data from varieties of EDA layout tools for importing PCB and packages. So this way you can through ECAD data, you can plot your traces. You can bring your traces on your PCB. So basically what it will do is it will import the trace data on your PCB. So transferring Icepack projects. So you can also transfer your Icepack Classic project to ADT Icepack. So how we can do is all we need to do is we need to save our project in the Icepack Classic project. That is the extension is known as .tzr file. So this file can be opened in any of the Icepack versions. .tzr file. Coming towards the Icepack meshing. So Icepack meshing offers a flexible automatic meshing. So it's a highly accurate body fitting machine for complex shapes. So what generally happens is in when we see on the other tools, or let's say we are performing or initial level user is performing a meshing, right? He is not much aware like where the meshing should be fine, or when at what location he can go with the coarse mesh. But when we perform a meshing in Icepack Classic, so Icepack has a different capability of meshing. So if you see on the screen, there are four different kinds of meshes available. So if we focus on the third part, right, the radial gaps. So this is basically your multi-level options to resolve fin gaps. So when you see the gaps between the fin, the meshing is very pretty much fine in the gap regions. Whereas if you see the outside or inside domain, the mesh is gradually increasing and there is no drastic change in the mesh. So it's gradually increasing its element size. So this is how it's automated in such a way like you don't have to worry much about meshing part. You just have to uh, perform the meshing, keeping in certain points in the mind. That's it. So apart from that, you can go with the non-conformal assemblies. You can go with the multi-level of meshing. These are few of the meshing methods which are available. And also you can measure HUD option is also available in the meshing part. So on if you see on the right hand side top, there are different options are available. That is automatic conformal cut cell meshing is there. Automatic cut cell meshing is there. That is for full model. Then you are having other options like you can decide the resolutions whether you want the coarse mesh, medium mesh, or fine mesh. So accordingly, the option will select, the system will perform the meshing in similar manner accordingly. So when we talk about the Icepack solver, so let's say we have given all the inputs, how the equation will be getting solved, in which solver it will be getting solved. So basically, solver is based on Ansys Fluent. It is the same solver which Fluent CFD solver is using. So it's already validated physical models with capabilities delivered fast, accurate results, and across the wide range of CFD application. Then, if we talk about the numerical convergence, so that is more robust and rapid parallel scalability with HPC is also proven. So this is how your simulation window will look like when your solution is running, and this is how you can see the post processing contours. So this is basically a contour. The above one, these are for the flow contours, how your flow is behaving with respect to your being or incoming flow or your blades, if we talk about the quadcopter. So coming towards the post processing part, so what are the different capabilities and what are the different things we can go ahead and do in post processing? So when we talk about post processing, generally it comes into our mind that we'll be seeing a colorful contours. That is not just it. All the graphical representation, whether it's your contour, whether it's your plot against your potential and time or temperature graph is there. These all or your velocity vectors are there. This will all come under your post processing part. So when we talk about the post processing, these are the different capabilities which you can go ahead with post processing. Our velocity vectors are there, temperature contours are there, fluid particle traces are there, isosurfaces, cut planes, XY plots, animations. These are various capabilities which are available. So when we see the velocity vectors, so on the very left hand side, you can see there is a graph, sorry, there is a contour for the fan. The 3D CAD is there, and inside there is a rotation, and you can see the yellow and the green kind of region is there. And here, if you can see, there are some arrows are showing up. So this is the contour for velocity vectors. So what this contours indicates is how your flow is taking up place. The flow is entering from this direction and rotating in this particular manner. So the rotation side, you can see if you want to reverse the direction, let's say this is flowing in the clockwise direction and your flow should occur in anti-clockwise direction, you can reverse your RPM. So this is how you can analyze whether a fan is performing in a particular way or not. Apart from that, when you see the second contour, which is there, the 3D projection of cut plane. So that is basically the cut section view of a PCB the on the mid section. So this will indicate your temperature profile and distribution on your plane which you have plotted. Apart from that, if you see the animation of temperature contours and fluid streamlines, so the fluid streamlines, when we see, these are the streamlines which are plotted on the very dead end, it's there, the blue colors one. So these are the fluid streamlines. So these are few of the other examples, animation of particle traces through data centers. Apart from that, overview, summary, and detailed HTML reports. So when we talk about the summary and HTML reports, these report contains your full simulation data. So when we talk about the full simulation data, it will showcase you what are the geometries you have imported or you have created in the Icepack itself. Meshing, what kind of meshing you have performed, what are the minimum maximum element size present in your meshing, whether it's the measure HD meshing, non-conformal, conformal meshing, all the data will be there available in your reports. What are the different input conditions, boundary conditions you have select, what are the physical models. When we talk about the physical models, I mean here is the turbulence models. What is the turbulence model which you have taken, how much time you have run the simulation. Let's say you are running it for the transient simulation, for how much time. Let's say you have run the simulation for 5 seconds or let's say 10 seconds, so it will indicate the simulation solution was run for the 10 seconds. And what are the different contours you have plotted, it will also include in that report. So it will give you an overall report from start to end, what are the different operations you have performed in the during your simulation. So additional options for model building is there are basically the libraries are present and the merge of project options are there. Library will be a standard electronic components are included with the Icepack. Your let's say your materials are there, blowers are there, components, fans, filter, heat sinks, all these things will be included in your library. When we talk about merge project, if you want to merge the two sections or two projects in a similar way, in a same window, that option is there for the merge projects. So that option we will be getting through files. So when we open the file, we'll get an option known as merge project. Then coming towards the macros. So macros are the standard features and functionalities that Ansys Icepack offers. So via specialized subroutines that is known as your macros. So basically macros are divided into the four parts: geometry, modeling, post-processing, and productivity. These are the four major macros which are present in Icepack Classic. So when we talk about the macros, you will get a different kinds of options available inside the macro. So when we talk about the modeling, you can see heatsink internal is there, IC packages are there, Icepack coupling is there. So these are the different types of macros inside the modeling part. Similar way in post processing and productivity, you will also get if your solution is getting diverse, so it will debug the divergence also. So these kinds of facilities are available in macros. Now coming towards the advanced modeling options. So when we talk about the advanced modeling options, so that is basically the multiple fluid modeling. So that is nothing but your multi-phase flows, right? So on the right hand side, top, you can see there is one of the geometry and your components are placed over top. Your three PCB components or board components, you can say, are placed over there. And there is a cooling channel designed at the bottom of that. So when the cooling channel is coming into the picture, so on the bottom there is a cold plate with glycol is there. So glycol is flowing around and your air is flowing in this direction, right? So these are basically the two fluids, air with respect to your glycol. So this kind of simulation. So here your glycol is entering and it will cool down this the bottom plate, and from top the air is coming up. So air will cool the top surface. So this kind of different uh, materials or multi-fluids analysis is possible. For such examples are cold plates are there, your heat exchangers are there. Apart from that, species modeling. So basically, if you see this is a, let's, you can consider this is as a parking garage, or let's say a data center is there. This is the full data center, all your data stacks are over here, present over here, and there is sudden fire from this point. So how your fire is going to, basically not the fire, smoke, how your smoke is going to take up to the top level, how the behavior of smoke will come into the picture. This kind of different uh, yeah, species simulation can you can do with the help of Icepack classes. Coming towards the automatic solar radiation with transparent surface media. So basically, when we see about the automatic solar radiation, so you can see the antennas are placed continuously on the outer surface or on a certain height. So it's 100% open in the air conditions, and the solar radiations are directly getting applied to on the surfaces of the your components. So for that, you can also select the solar load model. You can select the different solar models uh, as per the application. So all the properties will be fetched directly through the models and the solar load calculator. So these are few of the advanced characteristics for the solar model, and advanced turbulence models are also available, which I just shared in the previous slides, that K omega SST is there, Lens model is there. Your other other models are present, K optional models are there. Now coming towards the MRF. So MRF, when we talk about the fans part, so that is basically your multiple reference frame model. MRF stands for multiple reference frame. So what actually happens is when you rotate any part, your mesh will also rotate. So ideally for fan we have to create a moving mesh, but when we go with the moving mesh option or dynamic mesh option, it will take a lot of time and computational efforts to perform those kind of meshing. So for that, multiple frame reference model is available, which will act as a dynamic mesh only. But the your mesh is general mesh, not the moving mesh. The mesh, the region which will defined as a MRF, it will act as a rotating component. So this can be utilized with the MRF, and you can reduce your modeling time and simulation time with the help of MRF fans, and you can get the results as accurate as the transient simulation results. So you can also analyze the flow swirl, and the fan effects of the on the fan blade geometry due to your wind pressure. So coming towards the detailed thermal conductivity maps, this is basically for the PCB part. So thermal conductivity from computed from the imported ECAD data for a PCB. So this is how you can import and perform the simulation for the traces and your metal fractions. So you can import the traces from the different tools in Icepack, and then you can go ahead with the your thermal management simulation. You can check the electric potential, current potentials, and your joule heatings and the temperatures on your traces, like which traces get what is the actual temperature of the traces. Coming towards the electric joule heating. So when we talk about the joule heating, Icepack solves the direct current conduction as a part of CHT, conjugate heat transfer solution. So when we talk about the CST, you can see there is one of the on the left hand side, there is one of the contour is plotted. So that is basically the electric current density. Here you can see there is a fuse region or very narrow region. You can see here, you can see the highest potential or current density is highest in this particular region. On the if you see on the second diagram, so these are the potential contours of high current traces. So the regions where your high current is flowing and on the traces. So these are the regions for that. If you want to see the electric potential on the your PCB, this is how it will showcase you. This is the basically the region. It's where your electric potential is getting distributed, and the temperature on that particular distribution, what's your exactly the temperature on that particular region. So this is how you can plot your temperature contours. Coming towards the Delphi packages, so your Delphi network model is also available inside your Fluent Ansys Icepack Classic. This is the kind of room model is there. So basically, when we do the simulation for very complex or let's say on a large scale to reduce the computational time, we can opt for the room model, which is already inbuilt in classic version. So it will basically speed up your simulation time. And the ROM will be run on the steady state solution. So basically, this is the iSpec CFD process. So the your step one is the geometry, whether it's MCAT geometry or ECAT geometry import is there, or you have created your geometry using iSpec primitive shapes or dominant shape and size. You what are the different parameters or geometrical parameters you have given. Then coming towards the physics. So when we talk about the physics, so what we are concerned of in this particular region is we'll be deciding the kind of simulation analysis, like whether it's a steady state, transient, we'll be selecting appropriate physical models, whether the turbulence model which we have taken is right or wrong, the material properties or the properties of material will be defined in each and every different components consisting of different material properties. Then we'll be giving the boundary conditions. When we talk about the boundary conditions, we'll be giving the inlet conditions, outlet conditions, or let's say we'll be giving the heat sources for our MOSFETs are there, or like ICs are there, or heat sinks are there. Then we'll be giving the initial conditions, like if the flow is a natural convection, so we'll be giving it as a pressure inlet. Different kinds of initial conditions are present. We'll be giving those conditions. Then we'll go for the mesh creation. So when we go for the mesh creation, which kind of mesh we want to go with? Mesh HD is there, hexa unstructured mesh, Cartesian mesh is there, conformal, non-conformal. Different options are available. We'll be selecting the most appropriate option as per our requirement. Then we'll go to the solution. So when we go towards the solution, we'll see the convergence criteria, how much maximum iterations we want to go ahead with, what are the different solution monitors we can plot, numerical schemes, if the solution is not converging, what are the under relaxation factors which we can go around, single or multiple cores, and the parametric tier. Apart from there, we'll come to the post-processing part. So we'll see the plane cuts are there, cut planes are there, isosurfaces, various contours, vectors, streamlines, velocity plots, history plots, trial plots. So these are different kind of post-processing which we will be doing. Then coming towards the final step, that is the we'll see get the full reports, and we'll see the HTML reports are there, point reports are there, overview summaries there, what are the fans operating points. So these are the different reports which you can go ahead as per the requirement. So coming towards the multiphysics workflow with Ansys Icepack. So when we talk about the multiphysics, so this is the comprehensive capability of multiphysics with regarding the Ansys Icepack Classic. So when we talk about Classic, what are the different tools we can couple it with? So when we talk about coupling with other tools, that also indicates the different physics. So let's say you are performing the iSpec classic simulation, or you want to go with the coupling of electromagnetics, or you want to come from the PCB level and then you want to perform that particular PC in Icepack, you can take the results from there and you can compare, perform your simulation in Icepack. Or let's say you have already performed the simulation of PCB. Now you also want to see, like, you perform the thermal analysis of a PCB and you see this is my maximum temperature region, and you want to see whether this temperature can deform your PCB or not. So if you want to check the deformation, in this case, you need to go for the electronics reliability or the mechanical part. So to see the deformation. So what mechanical will do is it will take your Icepack temperature as an input in mechanical, and due to that temperature, how your material is getting deformed. That kind of simulation we can perform using multi-physics. So your heat data will be, temperature data will be taken as an input in the mechanical, and it will showcase you how the temperature is deforming or not deforming your structure with respect to the temperature input which you have taken it from the ice pack. So again, the twin builder is there when you want to go with the full system level of assembly. So when we say about the system level of assembly, let's take an example of a automotive domain. So let's say there is a battery. So for every batteries and powertrains. So when we talk about EV, so there is a powertrain which is driving the full vehicle, and the powertrain has been controlled by the BMS, and the batteries are also controlled with the help of BMS. So the full structure, including batteries, your structural part, your powertrain, your BMS, that will come under your system configuration. So when we want to perform this kind of simulation, we are also having the option of twin builders. Or let's say you want to additionally go with the ROM model, so you can go with twin builder as well. So these are few of the other capabilities which are present. So coming towards the Red Hawk Icepack, so Red Hawk Icepack generates the chip thermal model, that is basically the CTEM model, which is library of temperature dependent power and the per metal layer density information of a chip. So this kind of simulation, so for the PKG data or the chip data you want to see. So for this kind of Red Hawk Icepack is available. SI wave Icepack is there. That is for the current density plots which can be taken from the Icepack, and you can couple those with the temperature on the classic part. This is the Icepack and mechanical coupling which I just talked about, like how if you want to see the deformation, how your deformation is taking up places. So this is how you can couple your simulation solution results into your setup. So when we talk about the setup, your setup includes your initial conditions, your boundary conditions and all. And we have linked this geometry with this geometry in the structure. So from here it will take up your geometry as well. And here we can feed the material data. That is basically the engineering data or the properties of the material. We can feed it over here. So I spec with the Sherlock for PCB reliability. When you want to perform any kind of reliability test or strain plots and all, so you can go with the PCB reliability with the help of Sherlock. So now I think we will go with one. We'll see the tool UI. So this is how we can go ahead and open Ice package from the search. This is Icepack 24. So I'm already having one of the projects, so I'll open it up for first before that. So this is how your UI of Icepack looks like. This is your graphical window. These are the different, this is the basically your ribbon. These are the different tabs which are available. This is your basically known as your outline view on the left hand side. This is for the project and this is the library. So when you exclude your library, it will come like what are the different kinds of library already available. So from here file, you can open new project. You can open any of the project. You can merge your projects. You can save it from here, import and export your IDF files and your traces files from here. So when we talk about this project, so let's say this is one of the example which we are going to take. So this is if I just now I think the fins are also visible. So this is basically one of the heatsink is present over here and one of the fans is also there. So this is the assembly one vent is also present over here, and this is one of the your fan assembly. At bottom, if we see, there is a fan. So fan one is there and it's connected through tubes, and this is your heating component, basically your heat sink, what we say. So these are all your on the between the GUI and the outline view, there is a different primitives available. So if you here, if you see, it shows an option of create assembly. Here, create networks. Your heat exchanger is there. Your openings, create openings are there. Your periodic boundaries are available. Similar way, if you want to go with the PCBs, your PCBs here, blocks options are available. Enclosure option is available. Your power sources options are available. Your heat sinks are available. So let's see if I select this cabinet. So here are the location. So when I have selected the cabinet from here in the left hand side outline view, you can see the blue cabinet boundaries are highlighted, right? So uh, if you see on the bottom side, on the bottom left hand side, you can see here are the parameters through which we can give the input conditions. That is basically XS, XE. So what this XS and XE indicates is X in the axis is X-axis and the start point is 0 meters and the end point on X-axis is 0.65 meters. So this is how it will create your line or cube in the X, Y, and Z regions. You can define whether you want to go with the prism, you want to go with other options. So this is basically already prismatic type of geometry. So that is already a prismatic option is available. So once we create it, if we double click on it, double click on the cabinet, so there will be option of information. You can give here the name, your default line width and the colors. Right. Apart from that, if you go to the geometry, you can select the different shapes. If we go in the properties of wall type, we can select whether it's wall, it's opening or a grill. So in similar way, if we open the heat sink or let's say one of the blocks. So I open one of the block. So here block name is there. Here the shading is there, whether it's solid, liquid, solid on wire shading is there. Geometry type is there. So here if you can see, this is block. So block we get an option of cylinder, polygon, ellipsoid, cylinder, CAD. These are the different options which are available. And in similar way, if we go in the properties, we can select the type of block, whether it's solid, whether it's hollow, it's fluid, or it's a network component. So when we see about the thermal conditions, whether it's a fixed heat condition, fixed temperature condition is there, or internal condition is there, what is the total power, heat flux, the temperature limits, fixed values. But these are different kinds of options which are available. So this is how we can utilize it in the different areas as per our requirement. So what we'll see is this is one of the geometry, and now we'll see how to set up a problem in a quicker manner. So we have to follow this project view. So when we double click on the problem setup, this kind of setup wizard will get open up. And we can see for what we want to solve our simulation. Let's say we want to solve for the velocity and pressure, solve for temperature. We currently don't want to go for the individual species. So we'll select the required and then we'll move to the next. Then we'll select the geometry is having or your body or your component which you are going uh, to take consider for the simulation has inlet outlet or not, whether your flow is bouncy driven or natural convection or forced convection, so that we need to specify it over here. So we have already selected the force convection over here. The next time step will be to determine the flow region, whether your flow is laminar or turbulent. Then we have a wide range of turbulence models starting from the zero equation to equation RNG model, enhanced to equation K epsilon, RNG K epsilon. So these are the different turbulence models which are available. Then we will select the heat transfer, ignore the heat transfer due to radiation. So whether you want to consider the radiation part or not. So from here we can select the, if we want to consider the radiations, so we can include the heat transfer due to radiation. Then we'll go to the next step. If you have included radiation, you can include the solar radiation from here. Then there is the behavior, whether you want to go with the steady state or transient. So we can select it from over here. Then the adjustments are there, adjust the properties based on altitude. So let's say you are going for any components which are going to be fitted, electronic components, or let's say avionic components are there. So when we talk about the avionic components, they fly on, the components will be on certain heights, the altitudes. So based on the altitudes, the properties of the fluids and everything will get changed. So we can adjust the altitude properties based on the properties based on the altitude. So then these 14 steps are done. Then we can just click over done, and then we can go with the basic parameters. So basic parameters, we'll select what we have selected over here. This is in a tabular manner. This is the general setup which we have already set up. Then in defaults, we'll see the temperature, pressure, radiation temperature, what is our default fluid, so that we can select from here the fluids which we have defined, right? Then this is for the transient setup. So this is steady state. So don't have to give the start time and the end time. So this is basically a flow time. And then there is an advanced option, which will be basically the operating pressures and if it's the flow is ideal gas. So these all things we can select it from here. So this you can also find in the solution settings. This is basic settings. So when we go in the basic settings, here we will define the number of iterations. So for example, you want to go with 200 iterations, or let's say I want to go with for the 100 iterations. I will define the number of iterations over here, and I will select accept. These are few of the parallel settings. You want to go with the series, parallel, network parallel, or job scheduler. So this kind of parallel settings can be set up from here, and then there is an advanced option is also available. So when we go with the advanced option here, we can select the discretization schemes, basically pressure. So whether you want to go with the standard, second order, body force, or pressure. In similar way, you will be getting options for the momentum and temperature as well. These are few of the under relaxation factors. So this is, we generally don't play around with the under relaxation factor much. So this we will be keeping it as a by default itself. Then here the option is there for meshing. So when you see on this ribbon, there is a square box and grid over here. So if we double click on it, we can generate the mesh. So when we open the mesh control, we just have to select the mesh type. We can drop down and we can select the mesh as the unstructured or Cartesian mesh. Then we simply have to create the general on generate the mesh. So I've already generated the mesh. So what I'll do, I'll showcase you how to uh, start the run. So once everything is done, you can go in the solve model and solve tab, and there is an option known as run solution. So you can just click on the run solution. You can give here your ID, and you can start the select on start solution. So it will take around 2 or 3 minutes. So we'll see all your processes will be shown up here in this dialog box. You can say it is a console or your dialog box. So whichever process is going on, it will showcase over here. If you also save your project, it will indicate done saving. When we start the running process, the customs windows get open up and it will showcase you what are the iterations it's going on. So this is your solution residues bit. So if we see this graph is for the velocity point and this graph is for the temperature. What we generally observe from where this graph starts to get steady. Just we'll wait for now 25 to 30 iterations are already done, 25 iterations. We'll wait for 70 or 80 or let's see, let's wait for 100 iterations. And then we'll see the plots. It will take around 2 to 3 minutes only. It won't take much time. So meanwhile, if anyone has any of the doubts, you can ask. Your residual seems to be getting stabilized. Your temperature is stabilized, already stable. Velocity is already stabilized. You can see from 25 or 30 to 60, there is no significant fluctuations in your velocity profile. Your temperature profile is still fluctuating from here to here. That is basically from 40 to 60, but from 60 it seems, from 50 it seems to be in a stable manner. Fluctuation is not going very much up and down. Almost 80 iterations have been done. I'll wait for a minute until it finishes all 100 iterations which we have given. From 1995 iterations have already been done. If you want to terminate it or stop in between, you can just select terminate. So it will stop over that particular iteration. Let's say all the iterations have been finished. So we can simply click on done and we can see here I have already selected the heat sink. So it will indicate the minimum and the maximum temperature for the all the selected components. So let's say I want to see on this particular component, how can I plot this kind of uh, plots? So on the top, if you can see, there is object face and cut planes. So when I select the cut plane, if I enable the cut plane, here it will ask me the position of the cut plane. So I'll see, I want to see in the X direction. I will just simply display the show contours and give display. So on the left hand side, if you see cut one is there. So this is how your temperature is behaving in the particular region. In similar manner, if you want to see any of the temperature on your faces, you can select the face from here in objects drop down. You can select the all the objects which you want to see. So let's say I want to see for block 1, 5 and 6. So let's say I want to see in the pipe and joint 1, joint 2. I can select, I can give here accept and I can display show contours. From parameters, I can see change my controls for what I want to see the contour, whether it's for speed, pressure, temperature. So let's say we want to see go for the temperature. We can select this object and we can give OK. So it is particularly showing contours for the particular objects itself. You can see over here. So this is how we can go ahead with different kinds of post processing. So let's say if also I want to see how your cut plane is behaving in y-axis. So from here I can select y-axis through center. I can select contours. I can, if you also want to see the mesh over that region, You can select show mesh option, show contours option, and you can simply give display. And from here you can give done. So this is how it will show you. So this is how your meshing is. So it will also indicate you the meshing over that particular point and region. I am just focused for the heat sink, so I can select over here and I can select the heat sink components from here. I can select this base to base oil. I can select tools display. It will particularly show the component heat generation over this particular region which I have selected. If you want to, at any point you don't want to see any of the cut planes or in the other sections, you can simply deselect it and simply select. So this is how you can see different kinds of. मेट्रो से आप देखिए आइएगा तो 51 उतर के 52 उतर के फिर 51 पकड़ना पड़ेगा आपको, लाइन चेंज करना पड़ेगा, एक्वा लाइन से एनसीजेड तक आप आ जाएंगे जब, तो वहां से फिर आपको Vishal, can you mute the other participants as well? So this is how your Icepack Classic works for the thermal management kind of simulation. So anyone can go ahead if you have any of the doubts.
Hello.
Hello, Anjay.
Yeah. Yeah. I have one doubt about the cabinet. How to define the cabinet? In actual practice, if you see in your example, you have defined the cabinet and consider as a mechanical housing, right, for the instrument.
Right, that particularly depends on your geometry and your object. So,
But
uh,
okay.
yes, go
Okay.
ahead, go ahead.
Okay. So, like, let's example, if I have the mechanical enclosure, okay,
Right.
and I have all six wall or something like other
Uh-huh.
CAD geometry. During that case, if I want to consider that mechanical geometry particular, then how I should define the cabinet?
So for in that particular case, let's say you are having an housing. Inside your housing, you are placed your PCBs and your other electronic components, right? Am I right?
Yes, yes.
So that will basically be an enclosure. So that will act as an enclosure. So we'll be selecting the enclosure part and the dimensions which are actually your mechanical dimensions of your outer casings are that those dimensions will be considering over here. So
Mm-hmm.
it's the same dimensions which your outer casing is there. That will be considering it as a enclosure and then we'll be defining it as a wall. So let's say if there are two openings in the sense your airflow path is there. So from let's say two fans are connected and there are a few of the holes in the starting or grills. So we'll be defining accordingly. So if there are grills, we'll define the grills. If there are exhaust fans, we'll define the fans and rest all will act as a wall. So
Yes.
which will
So that is
be,
fine.
yes.
Okay. But what about the cabinet? Cabinet should be larger than the enclosure, or how it should be?
No, no, see, but if you are defining it the cabinet, so that will be your exactly the dimensions of your actual component. Let's say you are having a component of one by 1 meter. So the dimension of the cabinet will be 1 by 1 meter.
The thing here is I'm a bit confused because first just tell me in Ansys Icepack, whether I just run the analysis, I should define the cabinet all the time, or I can remove that also.
You can remove that also. You can also go with an enclosure.
Okay, okay, understand. So it will not impact on the results, right?
No, no.
Uh-huh. Okay. So it depends like whether I just wanted to define by cabinet or I have option for the enclosure also. Both will give me the same result.
Right,
Correct? Okay.
right.
Okay. Fine. Yeah. Thank you.
Anyone else is having any of the doubts, you can go ahead and ask. Also, I will drop my
Uh,
mail ID if in future if you are having any doubts or you want to know in depth. So we can always stay connected. So I will drop my mail ID in the chat box also.
okay. Thank you, Shubham. I just have one more query.
Yes,
Uh,
yes.
See, normally Ansys Icepack, it's the example which you shown. It is just a cuboid shape instrument, right?
Right, right. That is a
But
basically a
yes,
very basic example
yes,
because actually I wanted to run over here. So if I take any of the complex examples, it won't take this much time. It
yeah,
will
yeah,
take a lot of more time. So
yeah,
for
correct.
just this was just to give you a brief regarding how to set up a problem and how we can go ahead with the different options. What are the different capabilities available? So
E-
the focus was that.
Yeah, yeah, that's true. But
Yes,
if I
yes.
say like Ansys Icepack, then how easy it is to just deal with some complex CAD geometry? It's a bit complex to create the model and during the doing the mesh, or because in the
See,
cuboid shape, if it is just
right,
simple
right.
rectangular, the mesh is very easy, right?
Right,
So
right, right.
how easy it is, how user friendly it is while
So,
dealing with some complex
right,
geometry.
right. So when we talk about the meshing part, so it will take very less time to perform the mesh in Icepack as compared to other tools which are available. So even if you are having a complex geometry, it won't take your much time and efforts to perform a mesh. All the basically in this in if we talk about any other tool, we generally give the maximum element size, minimum element size, right? But when we perform the meshing in Icepack meshing, according to the geometry, it will by default take the minimum and the maximum element size according to the spacings between the two objects or three objects. Or let's say if heat sink is there, the fins of the heat sinks are placed on pretty much very less distance, right? 1 mm is there, 2 mm is there, depending upon the types of heat fins. So the tool will automatically refine the necessary regions where the gaps between the two options are or two objects are less. When it sees there is a no object, the area is open, it will automatically create a bit coarse mesh over there. So that is basically automated meshing. So even if your complex object is complex, it's easier compared to other tools to perform mesh on Ansys mesh, Icepack meshing.
Okay,
Yes.
fine. Thank you.